right, welcome to week 6 of 8 weeks, where we will be talking about Lewis structures. I wrote that in cursive. Do you guys even learn cursive anymore? I actually had to look up how to do the L because I forgot because it's been so long. But anyway, that's Lewis structures in cursive. The first thing we have to do before we actually get into drawing Lewis structures are basically a two-dimensional representation of chemical compounds, right? So we can kind of get their geometry. We don't see a three-dimensional structure, but we can see it on a two-dimensional piece of paper or a board to see how the elements are actually arranged in a compound. But first, in order to be able to do this accurately, we first need to know how to figure out the number of valence electrons in an atom. Okay, so valence electrons are really important, not only for Lewis structures, but just in general. The number of valence electrons represents how many electrons in an atom are located on the highest occupied energy level of that atom. Now, you don't need to really worry about that for our purposes, but what's really important is that these valence electrons will dictate what elements this atom will bond with, how many bonds it will make, what type of bonds, whether it's a covalent or an ionic bond. They all stem from how many valence electrons an atom has. So first things first, let's figure out how to determine how many valence electrons each atom has. Luckily, there is a nice little trick that we can use based on the periodic table. So again, this is my terrible drawing of the periodic table where we have our first two columns over here, the tall ones, and then we would have 6 tall columns over here on the right. We're not going to worry about this transition block again, okay? So in order to figure out how many valence electrons an atom has really, really quickly, you basically just count from left to right the number of columns it takes in order to get to the column that atom is in. So if it's located in the first column, it's got 1 valence electron. The second column is 2. Then we're going to skip these 10 and go over here. 3, 4, 5, 6, 7, and 8. Right? There are 6 columns over here on the right. So that's your 3 through 8. So the most valence electrons an atom can have are 8. And that's when atoms are the happiest. Okay? They always want 8 valence electrons. The ones that are in this column, that last column on the right, those are called the noble gases. They already have their 8 valence electrons. They are satisfied. That's why they don't take any charge. If you remember, the charge for that last column was 0 because they don't like to change the amount of electrons that they have because they already have the 8 valence electrons that are desired. Okay? Now, there's 2 exceptions to the 8 rule. It's called the octet rule because it's 8. The only 2 exceptions are hydrogen, which is the first element here, and helium, which is the second element here in the top right. Those 2 atoms are satisfied with only 2 valence electrons. Every other atom, though, you can assume will want 8 valence electrons, and that will drive what those elements do with bonding. Okay, so let's just do a couple quick examples. Let's figure out how many valence electrons these elements have. So let's do magnesium, carbon, and neon, and then I'll show you how to draw these valence electrons in our little picture format. So in a Lewis structure. So Mg, if you look at your periodic table, you will find that it's in the second column, meaning it has 2 valence electrons. Okay, so the way that we show this is in a Lewis structure, you'll put the element symbol And then you think of this symbol as having four sides, right? It's got the top, the right, the bottom, and the left, just going around clockwise. So in order to show how many valence electrons, you take the number and you just start drawing dots, one per side. And then once you get one per side, then you can start doubling it up, right? There's four sides. If you put 2 electrons on each side, that's 8 total. 8 valence electrons is the max that you'll have. So Mg will look like this, where we have one on one side, one on another. I always start in the top and then go clockwise around, but there's no real rule. It's just what I do. So carbon has 4 valence electrons. I'm putting E with a little minus sign as my abbreviation for electrons, so I don't have to keep writing it. But 4 valence electrons, so you'll draw your symbol, and then you'll put dots, one on each side before you double up any. In this case, you only need 1 per side. You don't even have to double up any sides. Neon. Neon happens to be one of those noble gases that has its desired 8 valence electrons already. So we'll put neon, the symbol in the middle, and then we'll go 1, 2, 3, 4, and then we start doubling it up. 5, 6, 7, 8. Okay? So that would be if all 8 valence electrons are there. Now let's do one tricky one that kind of pulls on stuff we did in the past. Let's do a phosphorus ion with a minus, let's actually do a -2 charge. Okay, a phosphorus with -2. So originally, if you look up phosphorus, you would see that it has 5 valence electrons, but now we have this charge to worry about. So what's this -2 charge going to do to the number of electrons? It's going to increase the number of electrons from 5 up to 7 valence electrons, right? That's the only way we're going to get that -2 charge is by adding 2 electrons. So now we come over to draw. We're not drawing 5 valence electrons anymore. We're drawing 7 valence electrons. So remember, each dot is an electron. So there's 1, 2, 3, 4, 5, 6, 7. Okay, that would be how to show 7 valence electrons on a single atom. Okay, so now we're going to take this a little further and draw Lewis structures, not just for single atoms like we just got done doing, but now for entire compounds. Okay, so this is kind of a stepwise process. You need to do this process in the order that we lay out here. So I'm going to write out the steps over here on the right hand side while I do the steps in an example over here on the left. Okay, so it's important to recognize that when we're drawing Lewis structures for compounds, we are only doing them for covalent compounds. Okay, so this is only compounds that include nonmetals, and they will be structured together with covalent bonds, so sharing of electrons. Okay, so the example I'm going to do over here is for a compound CF4. Okay, so I'll do all the steps over here and list them out over on the right. So the first thing you need to do is add all available electrons. And all that means, to be an available electron, that just means, is that electron available to make a bond? Okay, and so when we say available electrons, this is just the total valence. Okay, so the total number of valence electrons, but for all atoms that are included. Okay, so we have 1 carbon atom and 4 fluorine. So you're just going to look at your periodic table, figure out how many valence electrons carbon has, which is 4, and then how many fluorine has, and each fluorine has 7. And there are 4 fluorines, so that's a total of 28. 28 plus 4 gives us a total of 32 available electrons. Okay, so keep that number in mind. Then, number 2, now we have to arrange the atoms in a structure. So what we're going to do is put the central atom, or put the first atom listed as the central atom. And then all you're going to do with the rest is position them around the central atom. Okay, so something like this. The first atom listed is carbon, so that will be our central atom. And then I'm just going to put the 4 fluorine atoms just kind of symmetrically around it. Okay, that's kind of the goal. We want to get this as symmetrical as possible. Okay, so that's number 2. You put them in the arrangement with the central atom in the middle, all the others around. And then number 3, you are going to connect each atom to the central with 1 bond. Okay? Now again, these are covalent bonds, and we will signify them with a dashed line like this. But each dashed line, because it's covalent, means that each atom that's connected here with this bond is giving 1 electron to that sharing bond. Okay, so covalent bonds, they are sharing 2 electrons. 1 electron comes from one of the atoms, the other electron comes from the other atom. Okay, so they're sharing. We denote that with a dashed line, but it does mean 2 electrons. They're just being shared. Okay? So that's number 3. Connect everything with a bond, which signifies 2 electrons. Then, number 4 is we need to fill in the remaining electrons to give atoms 8. Right? That's the goal. They all want to have 8 valence electrons, so we need to fill in electrons with the dots, just like we did in the past, with the dots signifying electrons, so that every single atom here has 8 electrons, with the exception of hydrogen, which would only need 2. Okay? So, let's do the central atom first. Okay, let's make sure the central atom has 8 electrons. Well, it's got 4 bonds connected to it, and each bond represents 2 electrons. So 4 times 2 is 8. Carbon already has its 8. We don't even need to fill in more. But if you go to the fluorine, all the fluorine has right here is 1 bond. Now, it can have those 2 electrons because they're sharing, so those can count 2 electrons towards its 8, but it's still missing 6. So at this point, we just need to fill in 6 more dots representing electrons to give that fluorine 8 valence. Okay? We'll do this with each fluorine because they each need 6 more because they have just 1 bond, which is 2 electrons. Okay, so 2 in the 6 gives us the 8. Now, all atoms here have their 8 valence electrons. They are all satisfied right now. Now we just need to make sure we didn't make a mistake. So, now we need to kind of do a comparison. We're going to count all of the electrons used. Okay, so count all electrons used in our structure. And this is literally just counting them up. So we have 6, 8, plus another 8 is 16, plus another 8 is 24, plus another 8 is 32. So in this structure, as we have drawn it now, we have used 32 electrons. The last thing you need to do is make sure the electrons used is equal to the amount that we counted up originally. We used 32, we had 32 available, and so we are done. Okay? If they are not equal, so if not equal to available electrons, then we will have to add a bond somewhere. Okay? So we would have to add what we would call a double bond, because we would have to put two bonds somewhere in this structure. Okay? But you can only do that between certain elements. So you could only do that between the elements carbon, nitrogen, oxygen, phosphorus, and sulfur. Those are the only elements that you could actually add an extra bond. So notice fluorine is not even on this list. Carbon is, but not fluorine. So we would not be able to add an extra bond here. It's against our rules. And so we're lucky that our available electrons actually added up to the used electrons. All right, last thing I want to do today are just two quick examples using these steps that we just outlined. First one will be pretty simple, and then the second one will be a little trickier, okay? So let's do NCl3 first, and let's just follow these steps and draw our two-dimensional structure of NCl3, which would be called, good, nitrogen trichloride, perfect. Okay, so first, add all available electrons. So look at your periodic table. How many does nitrogen have? How many does chlorine have? You should very quickly see nitrogen's got 5. Each chlorine has 7, but there are 3 of them, so we have to add all of them up. That's 21 and 5 gives us a total of 26 electrons to use. Okay, so keep that in the back of your mind. And then go into number 2. Put the first atom listed as the central. So we'll put nitrogen there, and then I'll just put the chlorine around it like that. It really doesn't matter how you arrange them. But then connect each atom to the central with one bond. One bond, one bond. Fill in the remaining electrons to give 8. So right now, nitrogen has 3 bonds connected to it. That's 6 electrons because each bond is 2. So it only needs 2 more electrons to get up to 8. Each of these chlorines only is connected with 1 bond right now. So that's only 2 electrons. We need 6 more. So we'll fill in those 6 electrons around each chlorine. Okay. Now we have to count all of the electrons used. So we've got 8 around this chlorine, 8 here, that's 16, 8 here, that's 24, 25, 26. We are equal to the amount of electrons used, so we don't have to go on to this last step. We are done with this structure. So you can see the two-dimensional structure of nitrogen trichloride just by doing these steps. Okay? The last one we'll do is a little trickier. It is going to be CH2O. All right. So first, add all available electrons. So carbon has got 4, hydrogen, each of them, they're in the first column over there, so they only have 1, but there are 2 hydrogens, so we'll multiply by 2. And then oxygen has 6, okay? So if we add all of that up, we have 10 and plus 2, so that's 12 electrons to work with. Okay, so keep that in the back of your mind as always. First atom as the central, so I'm going to put carbon here. I'm just going to put the hydrogens on either side and the oxygen up top. Again, doesn't really matter how you arrange them. Connect each atom to the central with a bond, okay? And then fill in the remaining electrons. Now here's the first time we have hydrogen, right? So hydrogen only needs 2 electrons in its valence count. It doesn't want 8, it only wants 2. Well, each bond actually satisfies that. So each hydrogen has its 2, so we're good as is. But then carbon has 1, 2, 3 bonds. That's 6 total electrons, so it needs 2 more, okay? And then oxygen only has 1 bond, so it needs 6 more electrons, okay? Now, count all of the electrons used. Well, we have 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we have used 14 electrons even though we only had 12 to work with. So here's a problem. So if they are not equal, and this is the only way that they're not going to be equal, is if you used too many. We've used too many here. We need to, in turn, add a bond. And so this is how you do it. It has to be between 2 of these elements. So we couldn't put the new bond between C and H because H is not on this list. Luckily, we have C and O, both on this list, so we could add a bond, and we're going to have to. And so what you do is you add a bond, so just another dashed line, but when you do that, you erase a pair from each atom, okay? So now, if you go through and count, we have 2, 4, 6, 8, 10, 12 electrons. So we got this down to 12, which is good. And every single atom satisfies either the rule of 8 valence electrons for carbon and oxygen. Look, 1, 2, 3, 4, 5, 6, 7, 8. And 1, 2, 3, 4, 5, 6, 7, 8 for carbon. Or it satisfies the 2 valence electron rule for hydrogen. 1, 2, 1, 2. Okay? So that's really as hard as it can get. If you don't if you don't have the same amount of electrons used as available, then you go through that process of adding 1 more bond, and that will get you down to a new number. And if you're still not at the number that you need, then you can keep adding bonds, okay? So this could have been a triple bond as well if needed, okay? But follow these steps and you'll be able to do any example with Lewis structure.